Welcome to Mrs. Lee's Chemistry Academy. Today we are going to learn about solutions, specifically on the interactions and energetics of solution formation. Relating to the learning objective from College Board, that the students able to explain how solutes can be separated by chromatography based on intermolecular interactions. That the student can design and or interpret the results of a separation experiment such as filtration, paper chromatography, column chromatography, or distillation in terms of the relative strength of interactions among and between the components. Students able to apply Coulomb's law qualitatively, including using representations to describe the interactions of ions and the attractions between ions and solvents to explain the factors that contribute to the solubility of ionic compounds. Students can analyze the enthalpic and entropic changes associated with the dissolution of a salt using particulate level interactions and representations. Solution is a homogeneous mixture made up of a solute that interacts with the solvent through intermolecular force, and the solute is in smaller amount than the solvent. Their macroscopic properties do not vary throughout the sample. That means it's a homogeneous solution throughout. They can come in the forms of solids such as alloy is a mixture, liquids such as alcohol mixed with water, and gases such as air, which has 20% oxygen and 80% nitrogen. For aqueous solution, water is the solvent, and the solute can be a gas such as in your soda drink, which has CO2 dissolved in water, or liquids such as alcoholic beverages, or solids such as seawater containing salt dissolved in water. Liquid solutions consist of liquid that mix in all proportions, and if they mix well and you do not see a dividing line, it is called miscible. Liquid solution cannot be separated by filter paper. They have no components large enough to scatter visible light, so they are not a colloid. Components can be separated using paper chromatography, distillation, to overcome intermolecular force of attraction between and among the components. Paper chromatography. It is an analytical technique to separate colored pigments by partitioning the molecules over a stationary phase, which is the paper, and a mobile phase, which is the solvent. Now, paper is made up of cellulose that has hydroxyl groups that attract water to travel up. The separation of mixture is based on competition of the molecules' affinity for the paper, meaning how strongly they absorb onto the stationary phase, and for the solvent, meaning how readily they dissolve in the mobile phase. Separation is measured by the RF value, which is a ratio of the distance traveled by the molecule to the distance traveled by the solvent. The more soluble a molecule is in the solvent, the higher it will migrate up the paper with the solvent, and therefore the greater is the RF value. If the molecule is nonpolar, then it will not dissolve in a polar solvent. Now, the results of 4 different ink placed on paper chromatography paper are shown on the diagram on the right, and you can see there are 4 samples A, B, C, and D. Calculate the RF value of A. If we can measure with a ruler, the distance traveled by A is about 2.8, whereas the distance traveled by the solvent is about 6.5, so we're looking at that ratio. Which ink has a molecular structure similar to the solvents? Now, if you look at ink B, it travels the longest distance up the paper along with the solvent. Therefore, ink B is probably having a structure very similar to the solvents. Which ink has a greater interaction with the paper? If you look at ink D, that would have the shortest distance traveling on the paper, meaning that D is really attracted to the paper. So that's the answer, D. which ink has a greater interaction among the component molecules. As you can see, there are two dots for ink B and ink C, meaning that they have components in the dye mixture, and in dye B, the two dots are very close together. That means they have great attraction for one another. So here's a recap of my earlier discussion. The RF value is 0.28. And the second S is ink B that pulls the travels up along with the solvent. And 3 is ink D that travels the shortest distance from the start. And then both B and C have interactions between their components. Coulomb chromatography. It is an analytical technique. It separates components of a mixture based on differential adsorption to the stationary phase, which is the alumina or silica gel packed inside a column. So here's a diagram of it. As you can see, there's a column. Inside we packed it with silica gel, the stationary phase. Now then we pour the sample through the column, and then we pour the eluting solvent, which is the mobile phase, over the sample mixture from the top of the column. The stronger the intermolecular force, the stronger is the binding of the component to the silica gel, and the longer it would take for it to go through the column and be received in the flask below. The weakly absorbed component then will be eluted more rapidly, and by that we can separate components in a mixture. Distillation is yet another separation procedure. Here we have a flask containing a mixture of alcohol and water placed on a heating mantle, and the flask is covered fully sealed with a rubber stopper inserted with a thermometer so that we can read the boiling point of the liquid. Now when the liquid boils, it will turn into vapor, gas vapor, hot, that will travel through the condenser, and the boiling point will be recorded by the thermometer. Notice that the condenser is a double-layered tube. The outer tube would have water, cooling water circulating in it so that the hot vapor through the inner tube can condense back into liquid and be received as a distillate in the receiving flask. So once the alcohol boils over at 78 degrees C, now we have just water remaining in the flask, and the temperature will go up again until it reaches 100, at which time the water will boil, and then we can collect water as a distillate in another flask. And that's how liquids are separated by distillation. So distillation again is a separation technique based on different boiling points of liquid in a mixture. The stronger the intermolecular force of attraction between liquid molecules, the greater the amount of heat energy is required to overcome the attraction to separate molecules into vapor. And when there is sufficient vapor pressure present, and when it is equivalent to the atmospheric pressure, the liquid will boil. And we call that the boiling point. And the stronger the IMF, the higher the boiling point. Design a flowchart to separate a mixture containing iron, calcium carbonate, sodium hydrogen carbonate, which is your baking soda in the kitchen, ethanol, and water. So here it is. First, we would use a magnet to attract iron due to its magnetic property. So we take magnet out of that mixture. Now, the calcium carbonate is insoluble in water. Therefore, we can do a filtration and collect the calcium carbonate in a funnel fitted with filter paper. The other, sodium hydrogen carbonate, ethanol, and water, will be dissolved in the mixture, and then we can perform distillation and then collect the alcohol at a lower boiling point of 78 degrees C, and then water at 100 degrees C, and then now we have the residue of the baking soda, NaHCO3, left behind in the flask. Entropy, the driving force of a solution, is a measure of energy dispersal in a system. In other words, how random it is in the system. Nature has a tendency toward mixing to achieve greater randomness and produce a solution of uniform concentration. When two ideal gases are mixed, they have greater entropy than when they were in separate components. Just imagine if you have 1 liter of hydrogen mixed with 1 liter of nitrogen. Now you have 2 liters for the gases to roam around, therefore the randomness will increase. Enthalpy of solution defined as delta H solution. It really consists of 3 kinds of intermolecular force to be overcome. First, energy must be input endothermically to separate the solute into particles. Secondly, energy must be input endothermically to separate the solvent particles to make room for the solute to enter. And then third, there will be energy involved in mixing the solute with the solvent, and this is exothermic negative energy. Overall, the enthalpy of solution is the sum of the 3. Enthalpy of solution is equal to enthalpy of solute plus enthalpy of solvent plus enthalpy of mixing. Now here's a diagram showing how the particles can be pulled apart. If you look at the red and the green circles, they represent the solute which can be pulled apart to create room between them. And then below them are the blue circles representing solvent particles that can be pulled apart using the enthalpy of solute and the enthalpy of solvent, and this is endothermic. Now, as the solute enter into the empty spaces between the solvent molecule, this is enthalpy of mixing, which is exothermic negative. So the formation of solution depends on 2 driving forces, entropy and enthalpy. When we have the enthalpy of solute and that of the solvent approximately equal to the enthalpy of mixing, the enthalpy of solution will be 0. And the driving force is based on increasing entropy, randomness. However, if the sum of enthalpy of solute and solvent is less than the enthalpy of mixing, then the enthalpy of solution will be exothermic negative, and there are 2 driving forces in this: 1, the lower energy, and 2, the greater entropy. Finally, when the enthalpy of solute and solvent is greater than the enthalpy of mixing, then the enthalpy of solution will have a positive sign. This is endothermic. If the enthalpy of solution is too large, being positive, that means the solution would not form. Here's a diagram showing the enthalpy of solution. Looking to the left, you find that delta H1, delta H2, that's the enthalpy of solute and solvent, represented by the blue arrow going up endothermically. Delta H3 is the enthalpy of mixing, represented by the red arrow going down negative. So the overall enthalpy represented by the green arrow, enthalpy of solution, is exothermic negative in sign. On the right-hand diagram, you see this enthalpy of solute and solvent being positive going up, represented by the blue arrow. Enthalpy of solution of mixing, enthalpy of mixing being represented by the red arrow going down. Now the overall enthalpy of solution is represented by the green arrow going up. This is endothermic. Enthalpy of hydration is the heat energy change when 1 mole of gaseous solute ions is dissolved in water. If we look at the enthalpy of solution term, we can then combine the enthalpy of solvent and the enthalpy of mixing, and to let that be equal to the enthalpy of hydration. Enthalpy of hydration is always negative because the ion dipole attraction between the solvent and the solute is stronger than the hydrogen bonding that exists between the solvent molecules. In ionic solutes, the enthalpy of solute is equal to the negative of lattice energy. Remember, lattice energy is the energy released when ions mix together to form an ionic compound. So in this case, we're pulling them apart, pulling the ions apart, which is the reverse way of lattice energy. Therefore, it's negative of the lattice energy. When the enthalpy of solute is less than the enthalpy of hydration, that means delta H1 is less than delta H2 and delta H3 added together, the enthalpy of solution is negative, process is exothermic, and solution feels warm to touch, such as the dissolving of sodium hydroxide in water. Enthalpy of solution negative 57.56 kilojoule per mole. When the enthalpy of solute is greater than the enthalpy of hydration, that means the enthalpy of solution is positive and the process will be endothermic. Solution will feel cool to touch because temperature will go down, such as the dissolving of ammonium nitrate in water. Enthalpy of solution positive 25.67 kilojoule per mole. However, when the enthalpy of solute is approximately equal in magnitude to the enthalpy of hydration, that means the enthalpy of solution is close to zero and there will be no noticeable change in the temperature, such as the dissolving of sodium chloride to form sodium ion and chloride ion. Enthalpy of solution is very small, which is about 4 kilojoule per mole. Now, enthalpy of hydration is related to Coulomb's law, in the sense that we need to consider the distance between the ions and the dipole. The closer the distance, meaning stronger attraction between the ion and the dipole. And another factor to consider will be the charge on the ion. The higher the charge, meaning stronger attraction. And another one to consider will be polarity of the solvating molecule, the polarity of the solvent. The greater the dipole, meaning stronger attraction between the ion and the dipole. So here, leading to practice problem number 3. We have sodium ion, cesium ion, and magnesium ion. Enthalpy of hydration is given. Explain the relative magnitude of the enthalpy of hydration, why the way they are. Now, notice that sodium and cesium ions are having +1 charge, and cesium is a bigger ion than sodium. Therefore, sodium ion being smaller would have a stronger ion dipole attraction to water and resulting in a larger magnitude of enthalpy of hydration being negative 405 kilojoule per mole. And then with magnesium, it's a +2 ion having higher charge than the sodium and cesium ions. Therefore, it would have greater attraction to the water and resulting in a higher enthalpy of hydration, negative 1,922 kilojoule per mole. Practice problem number 4. The lattice energy of calcium iodide is negative 2,059 kilojoule per mole. Enthalpy of hydration is negative 2,163 kilojoule per mole. Now, what is the enthalpy of the solution? And write the stepwise equation. So the first thing we do is to write the dissociation of the solid, calcium iodide, into the ions in gaseous state. And enthalpy of solute is 2059 kilojoule per mole. Remember, this is negative lattice energy, so now we have a positive sign in front of it. Now the gaseous ion become dissolved in water. That's the enthalpy of hydration, and negative 2,163 kilojoules. So to calculate the overall enthalpy of the solution, we add up the enthalpy of solute to the enthalpy of hydration, resulting in negative 104 kilojoule per mole. To summarize what we have learned today, students have learned how to separate mixture in terms of using paper chromatography or column chromatography or distillation. And students have learned how to analyze the results from paper chromatography to interpret the interactions between and among the components in a mixture of dyes. Students also learned how to design a procedure to separate a mixture. We learned the energy involved in enthalpy of solution. We analyzed the enthalpic and entropic changes associated with the dissolving of a salt using particulate drawing and interactions. And finally, we learned the use of Coulomb's law to account for the enthalpy of hydration. From the team of MLCA, we would like to thank you for watching our video, and we look forward to seeing you again next time.